Lecture time. So over here we have the unit test for the synchronizer graph unit test. Here we have three different subgraphs, or three separate subgraphs: bulb, fish, and rock, SG0, SG1, and SG2. And they are all the same type, which are 4-point loops. Subgraph type 0, SGT0, 4-point loop. And as the name implies, they have 4 points, A, B, C, and D. Okay. And there's these synchronizers connected across them, these colorful lines that, connect up A, B, and C points together. Synchronizers can only connect across different subgraphs. They can't connect to the same subgraph, but they can't connect to two of the same points, or else it would lock itself, which I'll understand why later. But so subgraphs are kind of like state machines. They have a selected point, and they try to move on to the next point. But like unlike a state machine, which requires like a certain condition to move on to the next state, a synchronizer graph will just try to like cycle as fast as possible, and until it's stopped. Like, okay, a synchronizer graph would try to just run as fast as possible but it's stopped by synchronizers here. These colored lines, you see synchronizer 0 is stopping all of these subgraphs from moving to the next point. You see, because synchronizer 0 is like connected to these points, and now it's stopped the subgraph, and it's like, okay, it's kind of like a barrier or a gate, depending on on what you want to call it. But here they're called synchronizers, and they can represent like when dependencies aligned. Like, okay, it's currently time to read from vector A, and it's currently time to read to write to vector B. And yeah, and then once it's all aligned, we have to do something. Like, say we run a task, and then when it returns, we can unlock the graph to allow it to move again. Which here there's another synchronizer, synchronizer 1, which will keep A and B, bulbs A and rocks B in place, and only fish can move here. And then synchronizer 1 can unlock, and the next synchronizer 2. These two B's would get locked in place, but then A can move forward to B. And now synchronizer 2 can unlock. And here there's nothing connected to C, so these can just move on. Like, these can actually move out of order or all the same time, or all the way until they reach the next synchronizer. But the way that I coded the executor is to just move forward by 1 on each iteration, to just to like keep things simple. But technically, yeah, it can go out of order, it can go whatever, it can be multi-threaded, but as long as they align onto the next synchronizer, its behavior would be correct, and all the dependencies and stuff will happen in the correct order. And yeah, and here synchronizer 3 and 4 can unlock at the same time, and it loops around. But I don't think we have to do that. And on the next test case, it's kind of just like a tough case where there's only a single point. There's two separate subgraphs here, and it's called single point. It only has 1 point, called the only point. And there's foo and there's bar, 2 instances of the same type of subgraph. And a single synchronizer, you can't really see that it's locking and unlocking, but these two subgraphs are actually looping onto the same point, and the synchronizer in the middle is, locking and unlocking, because it's able to handle tasks like that. It's able to handle cases like that. And in this case, we have with the next test case, there's a what do you call this? There's 2 completely different types of subgraphs. We have the branching paths, which has 3 points, and branching paths has multiple different cycles. So the first one's called idle, which is just stays on the first point, stays on common, and just keeps looping the same point. Common. Next one is called via A, which would loop between, common A. And the next one's called via B, which is common B. And then there's a 3-point loop, which is just XYZ. It would continuously loop XYZ, XYZ, XYZ. And we've arranged the synchronizers in a way that we have something called schedule. And we have these two synchronizers in the middle that are currently disabled. And on schedule, we can just say, we just name it schedule. There's nothing that special about it. But we can just say that, at this task, whatever, at this point, we can make a decision to enable or disable or change a cycle. Enable and disable other synchronizers or change a cycle. So initially, this would just like loop around and not do anything. We see XYZ loops as expected, but common here just stays in the same point as expected. And eventually, we make the decision to enable with A or synchronizer 2 and change the cycle from to common A to via A. And yeah, now we kind of just like change the behavior of the graph a little bit. And the point of this is like being able to check if a vector is empty, and if it's empty, you can just not do anything, for example. If there's no requests, don't do anything. Or say, there's actually more complicated cases of like loop blocks in open space program where you can just like say you schedule a loop block and you can run a nested loop inside of another loop, and there's some really complicated things with there that I don't exactly remember, but actually I'll get to that eventually. But yeah, and here we eventually disable, we go back to idle. Well, actually, I accidentally leave this on via A. Like it's still going common A, but it doesn't actually affect the behavior that much at all. Yeah, it's still going to A. And then we eventually change to with B. So now it's going to go common B, common B, common B, common B, common B, common B. Yeah, and this, don't trust this. So I'm skipping the aquarium one because that's kind of confusing. But over here we have the process test case, which is an actual pipeline framework thing. Like it's not just raw synchronizer graphs. This is actually generated by the pipeline framework. So here we have, first at the very top, we have a subgraph called the block controller. And this is kind of like, you eventually have to tell like an application to start. And in order to like get into its loop and dependencies, there has to be some weird process of, say, like changing the cycles and stepping into there. And yeah, there's a lot of weird stuff that happens in a loop. Like I mentioned the actually I didn't mention it here, but the start of like there's no current start of the frame and end of the frame doesn't really exist. Like the end of the current frame is the exact same as the start of the next frame. The game loop is handled in a way that there's just no disambiguation between the two. But yeah, over here we have a block controller, has a schedule task. The schedule task determines, should we enter this loop block or should we not? And inside block run, there's two. You see those BC0 left and BC0 right along the top here. And this kind of encompasses all of the pipelines. Or like, yeah, these are pipelines converted into subgraphs on the inside here. And in this test case, we have something called process, which is feature process. We have 4 STD vectors of just integers. And we have 4 pipelines, which is process A, process B, process C, and process D. And each pipeline, each of these intermediate pipelines is what these are called. We have 4 stages: modify, schedule, read, and clear. On modify, we're allowed to write to the vector. On schedule, we check if the vector is empty, and then we read it. Read is when we read the vector's contents, and once everything is done reading the contents, you can clear the vector. Nothing's using it anymore. So yeah, schedule has this thing called schedule, and if it's empty, we can cancel all the tasks that are connected to the read. Like if the vector is empty, we don't have to clear it. And if I go head back to here, you see there's something called schedule main loop. That's just external finish. External finish is actually, instead of running an actual function, this external finish means that you have to the task is just gonna stay incomplete. It's gonna stay locked until you something externally would tell it to unlock. So if, say you have an asynchronous task that takes a long time to complete, you don't want it to to lock a thread. You don't want it to lock a thread. You just say, wait on this pipeline, and all the other subgraphs can still continue running. So here we have a schedule function that just checks if a vector is empty. This is just kind of like a generic lambda here. Copy function that copies from one writes to the other. And yeah, here we have the tasks. So copy A to B. This will read from process A, or vector A, and it would write or modify vector B. And then there's copy B to C, copy C to D. So it is kind of just like a chain of copy A to B, copy B to C, copy C to D. It's straight up is just a chain, and all of them have their dependencies synchronized here, sync with. And it's might be a little hard to see on a graph this graph viz generated thing, but there's something called sort of the guitar diagrams, because it kind of looks like a guitar. I've been calling them guitar diagrams, and the name kind of stuck. So we have the pipeline for process A, and we have these numbers. These numbers correspond to stages. So say on the modify stage of intermediate, the modify stage of process A, we don't do anything because nothing's connected to it. And when it goes to 1 on the schedule stage, and yeah, time goes kind of downwards here. Yeah, during the schedule stage, we run the schedule A task. And on read, we can run copy A to B. And you see process B is on modify, which is 0. So when process B, or vector B, is on its modify stage, and process A is on its read stage. So we copy from A and we write to B. And yeah, this moves on to 3 for clear, because after this task, we don't need to use this vector anymore. Nothing uses this anymore. We're done with process A. We're done with vector A, so we can clear it here immediately. Technically, this can actually go all the way down here or something, but it doesn't matter. And you see this kind of just repeatedly chains across until process D is still, on its modify stage here. And for the sake of the unit test, we have a check D, something called check D. The last task was run, which we just I think in the test that's just the assert or something. But yeah, when we run it, all the pipelines don't actually start. But actually, I didn't go over the how pipelines here are actually processed. Oh crap. So yeah, we have modify, schedule, read, and clear. And there's some C++ bullshit that you have to do to actually assign names to enums and give them some extra information, label them with use cancel and stuff. The string names are not actually used in code at all. They're only used for debugging. You can just names are ignored in normal operation. It's only the printing that we need information about this. But yeah, you see the modify, schedule, read, clear. You can see it. You see it up here. Modify, schedule, read, and then clear. You see task 6, copy A to B, is currently disabled because we're not inside the loop block yet. We didn't run the schedule task yet. Copy A to B, right? It reads from process A, which is, SGT2, PL0, with subgraph 2, pipeline 0, process A, right? And the next one is, subgraph type 4, which is the same. These are the same type. They're both the same type of pipeline. Every pipeline type is converted to a subgraph type. And yep, pipeline 1 is a process B. And you see that modify is connected here. Copy A to B. Read from A, modify B. And yeah, on schedule, we have schedule A. So we check if A is empty. Check if vector A is empty. There's something here called a task status, SGT1. Don't worry about that yet. It's kind of like it's related to being able to exit the loop block. I'll get to that later. But here we run the schedule task, which will enter the loop block. Everything starts on start. And then we want to make sure that all the pipelines kind of start at the same time when we enter a loop block. And then it jumps, sort of like jumps from the current cycle to the insides. And pipelines only have like 2 cycles. One is just start, finish, start, finish, start, finish. And the other one is, loop through all of its inner stages. So yeah, like he had these 4 stages: modify, schedule, read, clear. It would now loop modify, schedule, read, clear, modify, schedule, read, clear, modify, schedule, read, clear. And when an exit is requested, it would jump to finish. And the process of exiting can be kind of complicated. So like you see, the first thing that happens is schedule. The unit test puts some, initializes vector A with something. And it now checks, does vector A have anything? Which it does. And then it runs that. It turned into a dotted line over there. And then we can run task. You can now run copy A to B. And then we run that. And then we can now run clear A because we're done with A now. And we also check, is there anything in B? Because B is done being modified. And this just kind of repeats. This repeats, yeah, kind of goes down the chain. And yeah, since there's nothing that actually writes to process A, you see that it went all the way back to schedule now. So it's like we're not even done processing this part, and schedule A, and process A is already here. That's like one thing about the looping behavior, where there's no start and end of the frame. Like you can just have a task just loop around and run immediately, like whenever it can. Yeah, and then yeah, there's something called check stop that links together all of these scheduled dones. Check stop, check stop, check stop. And if an exit is requested, if we request to exit the loop block, which I don't actually remember where that's done, but it's actually when all the pipelines in a loop block are canceled, then it's gonna try to exit. And an exit is only allowed if this check stop synchronizer would lock, which you see there's this. It has to make sure that all the schedules are done. Because there was this weird thing where I can't actually tie together all the schedules with a single synchronizer, and I needed this intermediate task status subgraph. Like it was this really weird case that I had to deal with, and this was the solution that actually works out pretty elegantly. There was a lot of like janky ones before it. And yeah, once all of these are done, then we can jump. The states of the current pipeline states, like for these pipeline subgraphs, it doesn't actually matter what stage they're on. You can still jump to finish because, again, if everything's cancelled, ideally nothing is happening. So then we can all jump to the finish state, and that would be the end of the loop block. Yeah, and then the loop block right can finish, and then now it goes to block exit. All of these will just stay idle at the start state. I don't know why I have block exit here. I think there was something more important here before, but I just left it in there. And then finish. Block exit and finish. I don't even know why those are there. And now it goes around back to schedule. And then it can loop. We can I think it just runs the same thing. But here, I think it doesn't actually have any data. So actually, I'm not sure. Oh, and then is there another test? Is this a nested loop block? What is this? Nested loop test. And oh my god, this is really ugly. Yeah, so we have one loop block here, a block controller. And there's another block controller somewhere in here. Yeah, there's another block controller. I don't even want to like look at this. Oh my god, because yeah, we can have block controllers. Block controllers have a start and finish. Actually, I think yeah, this is what the block exit thing is for. Yeah, it's for that check stop thing from earlier to determine if we're allowed to exit. So in order for the outer loop block to exit, the inner loop block has to exit. Oh my god, there's so much lines. This is kind of like a subway map or something like that of a really big city. I've never been to like a city like this. Actually, I might have, but block left, block right. Like an Asian city, you know, they have so many trains. And yeah, here we have block run. You see this at the left, BC0, right? Going to finish here. Where's the left? Left is up here. Left goes up and then back down to there. So like this loop block is that pipeline, and like, oh my god. Oh my god, oh my god, oh my god, oh my god. So the inner loop runs, and then yada yada, then it exits, then that exits. And then it runs the inner loop. Again, I don't even remember what it does here. But yeah, nested loop blocks it's not, maybe not a requirement all the time, but there's a lot of systems within OSP that very much required this system. Required nested loop blocks. And there's some, more specifically like this, the link system, the circuit simulator in there, because it's like you have to like continuously run another process until everything is up to date. But yeah, I think that's all I'm gonna go over for now. How do I stop this?